Welcome to our third lab's second part. Previously, in part 1, you learned about variable data types, I/O functions, both analog and digital, and time functions, all of them as parts of a standard library. In this second part, we will complete our overview of essential standard libraries by presenting the available mathematical and trigonometrical functions. You will also hear about control structures for programming Teensy, and you will also see how to do in practice the digital analog and I/O operations. Let us start with the math-related functions. With improved hardware characteristics, Teensy exploits the potential of existing libraries and functions for Arduino boards, which include a large amount of mathematical functions. These can be used for simple calculations to quickly analyze the voltage of one pin compared to another, or more advanced functions, such as to help robots move around and calculate the best path available. Min returns the minimum out of two numbers passed as its parameters x and y. Note that the two values can be of any numerical type, for example, int, byte, or long, returning the same data type as that of the parameters passed. As you may guess, max works likewise to min, only it returns the maximum out of two numbers passed rather than the minimum. Again, the two values passed can be of any numerical data type. Function constrain constrains and returns as a result the value of parameter data to a set range set by some minimum and maximum values. ABS returns the absolute value of a parameter number x. PAL raises a number, parameter base, to the power of another number x, parameter exponent. Note the following. The type of both the base number and the exponent is float, hence allowing fractional exponents. However, the result is returned as a double. SQRT calculates and returns the square root of a number x, which can be of any numerical data type. Again, the result is a double value. Random returns a pseudo-random number that is always of type long. It has two parameters, min and max, that specify the range of the random number expected to be returned. If parameter min is omitted, then min is implicitly considered as 0. Thus, the result is a number between 0 and max. These are the functions used for three commonly used trigonometrical functions: sine, cosine, and tangent. Notice that all functions expect to be passed with an angle parameter in radians, and that they return a double result. Now, moving on next, we got code structures. As you will see, the structured programming paradigm improves the clarity, quality, and development time of a program by using structured control flow constructs of selection and repetition, and so forth. The power of Teensy is its ability to process data. It follows instructions and can execute a conditional instruction dependent on data. These instructions come in the form of conditional statements like if, for, and while. The if statement is the simplest one out of all branching statements. It is used to detect if an expression is true. For example, if some variable is equal, greater, or lower than a value. An if statement can contain multiple instructions within it, statement 1, statement 2, and so forth, which are placed inside curly braces. Let us check some examples which will help you understand logical operators, and specifically, the first one is equals. Important: do not confuse the logical equality operator, which is a sign with two equal signs, with the single equals operator, which is used to assign a value to a variable. For example, int I is initialized with the value 5. The second one is different than. using an equal sign right after a preceding exclamation mark. The third one is greater than. That's the usual sign that you're used to. The fourth one is less than. Again, the way that you know it. Note that there is also a combination of the equal sign and the greater or less than signs for the cases of 5, greater than or equal, and 6, less than or equal. If allows to execute two sets of instructions, as in the example of the slide's figure. This is known as an if-else statement. The program performs one specific action, statement A, if and only if the expression is true. Otherwise, it performs another action, statement B. Note that many times it is desired to use else if, or even to nest multiple if statements within others. The while loop statement is used for looping, this means for repeating, over the same code as long as a condition is satisfied. The condition is checked before the beginning of a loop, thus no loop may start at all. A for loop statement does the same job, this means repeating, yet in a different way. An increment counter is usually used to increment and terminate the loop. The syntax comprises some initialization, condition, and increment. The initialization happens exactly once before entering the for's code. Then, for each loop, the condition is tested at the beginning, and if true, then the statement block is executed, followed by the increment. And then again, before the next loop, the condition is tested again, and so forth. Now let us see how the functions you've been taught so far, as well as the control structures, can be used to write more complex programs on Teensy. But before we start, this diagram shows Teensy 3.6 along with its pins identified. To learn more about the pins, you should search for Teensy 3.6 pinout configuration. I recommend using the hyperlink on the slide, even though you may find plenty of alternatives online after a bit of searching. In brief, pay attention to the analog ground, abbreviated as GND and pointed with a black arrow, and the 3.3 volt output, pointed out with a red arrow, which we will be using in combination with other pins in the examples next. Another important point is to connect the Teensy on the breadboard so that the pins get well inside the breadboard. And now we will start first with writing analog signals, thus causing a LED to fade accordingly. How can you control the brightness of a LED? To do so, you need to supply the LED with voltages within the range of 0 to 3.3 volts. Analog output values in most microcontrollers can be emulated using pulse width modulation, PWM. In what follows next, you will use Teensy's PWM pins to control the supply voltage, in other words the brightness, of an external LED. On this slide, you can see the connection diagram with the Teensy on the left and the breadboard setup on the right. The material will include wires, one small resistor with a nominal value of 22 ohms, and one LED. Notice that we will use pin 6. On this slide, you can see the code. Notice the use of pin 6. This is set by int variable LED pin. In function setup, we indicate we will use Teensy's maximum baud rate, which is 9600. In function loop, we print a message for each loop. Then we have another loop using for looping, which changes the fade value loop variable from 0 up to 255, including 255, using a loop step equal to 5. Notice that the fade value step variable is increasing. Within the for, we use analog write, indicating which pin is used and what analog value is used in the loop round. we introduce a 50 millisecond delay at the end of the loop. When the for loop finishes, the same concept is repeated with another for loop, only this time by initializing fade value to the maximum value, 255, and unlike before, reducing fade value by a step of 5. Now let's try to see things in practice. This is the breadboard. The Teensy is on, and the setup that we follow is logically the equivalent one of the one that you saw on the slide. Now what I'm going to do is that I'm going to connect Teensy here. You see that the light is turned on. Now I'm going to verify, in other words compile. I'm going to upload the code, and as you can see, the light is fading. Now it is worth noting that if you start playing with the variables over here, you will see a different behavior. Let's turn the step from 5 to 50. And you already see that the behavior is different. Now, another important thing is that by clicking the serial monitor, you should be able to see the printouts. Now, let's try to add a little bit of more delay. Let's try to triple it. Verify, upload, and you see that it behaves differently because it takes more time to fade. Now, if you want to make it even more easy to observe, you just increase the delay. It might also worth increasing the fade value, in other words, the step, and obviously also the rate of printouts is different this time. This is because of the rate of the output being greater compared to what it used to be before. Our next example regards controlling a LED with a potentiometer. Specifically, you will learn how to read analog signals, such as the output voltage from a potentiometer, and plot the results using serial output. The connection diagram is on your screen now, with pin A0 being pointed out with a red arrow on the Teensy 3.6 figure on the left. We only need wires and a potentiometer for this example. And this is how the code looks like on the left, and a snapshot of the serial output messages on the right. As you can see in the breadboard, we have connected A0, which is for analog readings from Teensy, with this side of the potentiometer. The other pin is connected to the ground and the other one to the 3.3 volts output. I will connect the Teensy. Then, as you can see, I'm going to verify the code, upload it, and I'm also going to see the serial output. Now, what you currently see is that the serial output gives us the maximum possible value, and this is because we have the potentiometer set to the maximum possible value. I'm going to change this, and you can see that as I'm turning the screwdriver, there is a difference in the analog readings. So I'm doing it slowly so that you can see that. If I do it all the way up to the end, it will turn to 0. Now let me add a little bit of more delay so that it's easier for you to see it. I'm going to add half a second of a delay. Now this time, you will have more time to read the readings. In this next example, you will modify the Blinky program so that Teensy's LED is turned on and off depending on the state of the potentiometer. In fact, the max voltage by the potentiometer is the equivalent of a push button being pressed, whereas mean voltage is the equivalent to a push button being released. Therefore, this example can also work with a push button instead, sending digital input to Teensy. This is the connection diagram to follow. You will use wires, one potentiometer, or equivalently one push button, and a 22 ohm pull-down resistor. And this is how the code looks like on the left, and a snapshot of the serial output messages on the right. Let us first start with the potentiometer. What you see on the breadboard is the equivalent of the connection diagram you saw earlier. We get the ground, and then using a resistor, this is where we connect it to the pin of the potentiometer. We have the 3.3 volts connected over here, over this rail, goes to the other pin over here, and we connect the third pin of the potentiometer to what we call in our code the button pin, which is pin 24 of Teensy. And then, as always, compile it and upload it. You will notice that it's turned on. Moreover, if we use the serial monitor, we can verify that we got a closed circuit, and this is because it works right now like a pushed button, in the sense that digital write sends the highest possible value. Now, what happens, you can guess, when we turn it to the lowest possible configuration of the potentiometer is that the LED turns off, and at the same time you see that the readings on the serial output is off. Now, adding a little bit of delay to see things more clearly. Being printed, won't change much. You will see the same effect. Now you see slower that it's being printed as off. Now if I change the potentiometer, it will turn to on, and the LED obviously is also on. So the way we've done it here is essentially writing digital and reading digital signals. Now let's do that by using a push button. I have moved things a little bit around so that we can use a push button. Once again, you see that pin 24 is being connected, and this is our resistor leading to the ground, and we get the positive connected over here. Now what I'm going to do is that I'm going to connect my Teensy again. Perfect. And it already started, as you can see, but let me do it properly. I will verify it. I will upload it. And let us see also with our serial monitor what's going on. Now you see that continuously here you got off being printed. Well, if I push the push button and keep it pushed up until I release it, now obviously it's on, and you can also see it over here with the LED being turned on. If I release it, then the LED turns off, and then again you got the reading on your serial output being off. Now to make things a little bit more easy to follow, you can add some delay. Let me add a half second of the delay. I will verify it and upload it. And I'll go back here to my serial output where I'm going to clear things. Pushing it does what we want. Finally, now that you know how to write and to read analog signals, it is time to put this knowledge together with activity 3.2 and use analog output voltage from a potentiometer to control the supply voltage and thus the brightness of a LED. Your task includes using the connection diagram and the materials shown on this slide, writing, debugging and running the necessary code on your Teensy that also prints the potentiometer readings with the help of the serial monitor. And with all that, we reached at the end of Lab 3 Part 2, as well as at the end of our offline lab teaching sessions. To wrap up, in Lab 3.2 you have learned about mathematical and trigonometrical functions, control structures, and saw in practice how to do digital and analog inputs and outputs.